So my name is Marc Miltenberger, and I will present you an extensible and scalable architecture for hybrid analysis. Hybrid analysis meaning that we combine static and dynamic analysis. I will focus on Android here. This work was done in a joint fashion with Stephen Arzt, who is also my PhD advisor. So an overview of this talk. So first of all, I will show you the motivation of the work and the goals we wanted to achieve. Afterwards, I will present you the challenges we encountered and give you a technical overview and our approach. Then we will dive into a short demo, and I will conclude the talk with a summary. So what you can see here on the screen is a vulnerability which we found with our commercial vulnerability scanning tool called WUSC. And in this case, you have a vulnerability which basically is around an insecure HTTP connection. You can see the URL. Can you see? Yeah, you can see the URL right here. So the interesting part at this point is the reason why this is a vulnerability at all is because it's an HTTP connection, right? It's an insecure connection, and you need some kind of analysis to tell you that. So in order for the vulnerability to be found, the analyzer needs to have some sort of value analysis in order to get that information. In this case, we have sensitive data which gets saved into the preferences file, in this case a shared preferences file. You have the data flow between the two. So you have a clipboard data on the one hand side, which may contain sensitive information. For example, if you use a tool like KeePass or something, password manager, and then your password gets saved into the clipboard for a short time. So in this case, the analyzer needs some sort of data flow information. So vulnerability analysis often needs this kind of information. They also usually need a call graph information, which tells them which statement or which method may call which other method in order to do their work. And of course, for static code analysis, we have plenty of existing frameworks which can help with at least parts of these problems. You have, for example, FlowDroid, which can provide data flow support, and you can also generate a call graph with it. It's based on the SOAP framework, which is rather popular for Java and Android-based analysis. And there's also ICTA, which can provide you with support for intent component resolution, which is necessary if you want to know which Android component talks to which other. But to our knowledge, there's no real dynamic framework which can basically give you this kind of information and integrate nicely with static tools, because you have, on the one hand side, you have your dynamic analysis, and on the other hand, you have your static analysis, and they both live in different worlds and have different kinds of abstractions, basically, different kinds of data structures. When we are talking about the dynamic aspect, the dynamic parts, you have basically two different options. You can either modify the runtime environment or change the app you're analyzing. So the first option is to modify the runtime environment. For example, Taintdroid does this, which is a rather old approach from 2014, as far as I know, which computes taint information, so it's a data flow problem. And with this approach, you have the advantage that apps which have anti-tampering measurements, their checks do not trigger because you do not really change the app, right? You leave the app as is, and you only change the runtime environment around it in order to measure the values you want to gather. The disadvantage is that you are really inflexible in terms of real device usage, because as you're changing the system, you cannot really you cannot really install these change system on real world devices that easily. And in case there are updates to the system, for example, the new Android version comes out, you have the problem that you need to adapt your approach. The other way is that you can instrument or change the app itself. There are, of course, plenty of examples for this. For example, Taintman, which uses some kind of Smiley representation to change the app. The advantage is that you don't need to change the environment, so there's no routing of the device required. as it is in several of the runtime environment approaches. And the disadvantage is mainly you have the anti-tampering checks will prevent you from really analyzing the app. You can also do, you can either do a binary instrumentation or source code instrumentation. For the source code instrumentation, you obviously need the source code, which is kind of a disadvantage. So we went with the instrumentation way, and we want to do it with SOOT because FlowDroid is also based on SOOT, and as FlowDroid is a static analyzer, we can use our new tool to integrate nicely with FlowDroid. So the goal is basically that you have a beefy computer which does all the static analysis work, because you don't really want to do that on a phone. And after the static analysis is done, you have your you have our tool to instrument an application, create a new application basically, which changes the way the original application worked, in order to measure the interesting values. And then you let this new application run either on a single device or on a device farm, as you can see on the right hand side. We are referring to our older publication dfarm, which in turn has an approach in order to handle multiple or hundreds of devices concurrently. And when you run this changed application, it measures the interesting parts and sends events about these back to the host computer. And the static analysis can, at a later point in time, incorporate these results from the applications. So from a practical standpoint, you have a problem when you are concurrently interacting with many devices. As I said, this dfarm handles most of that, luckily. You have a communication between the instrumented app and the host computer in some form. We use ADB's port forwarding in order to generate, to get a network connection between the two, and use Cryo for the message serialization between them. For these anti-tampering checks I mentioned earlier, we try to change the respective code which does the anti-tampering check and pretend to be the original app. For example, if the application queries for the signature of itself, which it can do in Android, then we just return the value that it would expect instead of the real one. Another topic is, in terms of dynamic analysis, is UI exploration, because coverage is always a thing with dynamic analysis. We consider this problem orthogonal with our work, so for us, we were using some basic UI exploration tool like Monkey, but you can also click in the apps yourself, basically, if you want. So our approach is rather simple. Actually, it looks more complicated than it is. So we have a plugin-based modular architecture, and we have different types of notification factories, we call them, which are basically handling the different types of problems we want to solve, like call graph values, chain tracking, and they create a new instance for each app that we want to instrument, and they get queried by the dynamic value instrumenter for their logging points. Logging points in this context is borrowed from the publication of Harvester, which really just means an interesting point in the program according with some values and some minor details which kind of stuff is interesting at that point. The value instrumenter comes up with an instrumentation plan, which is an actual a plan of things to change in the original app. The app gets instrumented, and afterwards we run the app, either like on a local device with ADB, or on a device farm as shown earlier, like the hundreds of phones basically. And you can decide if you want to do it like directly, so you want to interact with the app by yourself, or you can use a dynamic input generator like Monkey in order to click in the app for you, so that you don't have to interact with each single application. The device communicator is instrumented into the app itself, and basically generates the interesting events. We will see some examples later. And these trace events are basically sent to the value handler, which acts as a sort of broker and sends these events back to the value notifier, which in turn uses these results in order to generate the things we are actually interested in, such as the taint graph, the call graph, and so on. So how do we actually measure, or how do we send events from the dynamic call graph? So we have a simple sample right here. On the right-hand side, we have like simplified Java code, basically. As I said, we do it on a binary level, so it's not really Java code, but yeah, that's just for the sample purposes. So for the call graph, we want to know which method calls which method. So what we do is at the start of each method, we basically instrument a special statement which sends an event which is associated with a special number. This number is a logging point number, and each point in the program basically has their own ID. And we have a mapping of the ID to the respective method, and we know which is which, basically. And we gather these events basically when the set event function is called. We have a list of events to send, and basically we group them together per thread. So we have a thread ID, we have our process ID, and we basically send all events in bulk, so that we don't have to send each event separately. And at the end of each function, we have an exit method call, but this is not really. This would be sufficient if we would only care about our own code, but we also care about system API calls, and for those we have the problem that we cannot instrument those, right? Because they belong to the system, so we cannot easily instrument them without rooting the device. So therefore, we use a combination of call and return calls. So before any function is called, we instrument a special call event, and afterwards we instrument a return event. And with this information, we get a complete picture of what the app is doing from a dynamic call graph standpoint. We can build a shadow stack on the computer, on the host computer, and therefore we know what each thread is doing at all times. For taint tracking, we do something which is a little bit easy. We do track our objects based on their identity hash code. So the identity hash code is basically an integer value which gets generated by the virtual machine, which should be rather unique for each object, but they may collide at some point. But we use them to distinct different objects from each other. And when we have, in this example, we have a value x, and this value x gets tainted at this point, and therefore, as we know, get sensitive data is a source function for us. We will just use the identity hash code of x and send that as a return ID as an event back to the host computer. So basically, for this event down there, the return ID would correspond to the identity hash code of the object x, and the other object IDs would be 0 in this case. So what taint tracking is also interesting in some cases, because you have the taint transfer. So if you have, for example, this line right here, in this case, a field gets tainted too, right? But also the foo object needs to be tainted, because in this case, we want to propagate the taint further, and the way we do that is we send a special event where we not only send the identity hash code of the tainted object, but also of the newly tainted object. In this case, we have some optimization that we have a set on the device where we keep a list of all tainted objects, so that we don't have to send every ID every time something could have been tainted. So in this case, we only send the necessary events in order to save some bandwidth. For dynamic values, like I showed in the sample with the URL earlier, the structure is a little bit different and depends largely on the type of value we have. So in this case, we have an example with reflection. Reflection is a way in Java to call arbitrary methods by knowing their name, basically, which can be passed on via string. And as reflection can be used to call essentially any method whatsoever, they are rather interesting from an analysis standpoint because resolving reflections is very important so that the analysis can understand what the program is actually doing at this point, because any arbitrary function could be called. So in this case, we are interested basically which actual method lies behind that. And for this one, we have basically have a model where we say, okay, for the method we need the actual class which gets called, and the method and parameter types, method name and parameter types. And this kind of information gets extracted and sent back to the host computer so that the host computer can deal with it. So I've prepared a video clip where I interact with a random application I found on the Play Store. Actually, I'm not entirely sure what it does. It tries to connect to some endpoint. Oh, you can't see it. Oh, yeah. I should. Yeah. Okay, wait. Yeah. Okay. So yeah. Yeah, as I said, this application basically tries to connect to some endpoint. I've just entered dummy values there. Yeah, the connection will fail, but that's not really a problem. We are just interested in the call graph and in the value it generates. So in this case, you can see all of our call graph events, but basically which method is calling which other method in the program. There are quite a lot of events, of course. And for the values, you can see we were interested not only in URIs, but also, for example, in load library calls, because these lead to new code being loaded. So the analysis also may want to analyze that newly loaded code, which is why it is interesting. We are also, why is it restarting? What? Okay. I just hit pause, I think. Okay. We are also interested in the files, and you can also see some reflective calls right there, which we for which we now know which kind of methods get called. As I said, the static analysis can use this information to augment its own call graph, and may use it to further get better results. So. Yeah, I don't think. Oh yeah, that's okay. I'll scroll through that a little bit. So there are quite a few events. We also have a demo plugin which allows you to incorporate your own analysis. This demo plugin right here is rather simple. So you can basically gather the information about the call graph, for example, and the scroll bar indicates that there are rather few edges, but keep in mind that Eclipse tends to limit the number of characters displayed. So yeah, there's quite a few more edges, as you can see in the console. And I can also get a list of each found data flow, and for each data flow, we also have the statements which belong to that flow. So we can basically see each statement which took part in that flow. So yeah. Okay. So to evaluate our approach, we took 1,000 real-world apps from the intro through, which is basically a repository of Google Play Store apps, and our metric was that if the apps worked also after the instrumentation, so they didn't crash and they produced events, then everything is all right. And everything was all right. You can see in the table like the number of different events per application. So the call graph, there were quite a lot of call graph events, just as expected. But you don't really need that much information per event because we group them together. So yeah. We have, due to instrumentation, we also have, of course, an overhead because we need to insert new statements. The taint analysis does quite a few more statements per app, but it does not really lead to much events, as you can see, because we do the filtering in the app itself. So we don't only send the taint events in case something gets tainted, and not always. So yeah, ultimately we have a quite significant increase in terms of statements, but since no app crashed, it means that the apps might be a bit slower, but it's all right basically. Yeah, that's basically it. This app runner framework, which I presented, can be found partly on GitHub, at least the demo code. Evaluation code. In order to run it, you need to have the WUS commercial scanner, but you can access it when you contact us. So yeah, you can try it out if you want. Thank you much for listening, and I'm open for questions.
Thank you very much. So we have time for one quick question because we are running out of time indeed.
You had an example where you're doing the dynamic taint tracking, where if a tainted value was stored in a field, you kind of communicated that the whole object is tainted. Does that mean that you lose field sensitivity, or?
Yeah. Actually, the sample was not well chosen. Yeah. So in this case, we lost the field sensitivity, but yeah. Usually we wouldn't really. So yeah, the sample code is not that great actually. Okay. to be fair. A better way would be if there was some kind of string builder append or something, because for the field actually we wouldn't really sensor trace the sample is not correct at the point.
So I have another quick question. So essentially in your evaluation, you automatically evaluated if the app was crashing. Did you make any manual evaluation to see if there were limited functionalities? Because in my experience, when you repacked an app and maybe this app is communicating with the server, then it works, but then it communicates with the server and the server says, look, I don't know who you are, I'm not trusting you. So not an error, but you don't have that functionality.
Yeah. So we also took screenshots of the apps, and I looked at a bunch of them, and it seemed to be fine. But yeah, in the case, I've also encountered some places where basically the login didn't work or this kind of stuff, right? Exactly. But we figured like, okay, well, that's all right. You can use another UI generation tool in this kind of things. So login detection is also an interesting research topic maybe, because for example, banking apps are usually protected with this kind of thing, and you can't really get past it easily. So yeah, you need to have some human intervention.
And luckily, they cannot get past easily. Otherwise, they could be hacked. Okay.
Yeah, sure. I mean, banking apps is kind of special, but also other apps do require login, for example. We did, however, install the Facebook app and logged in there as well, because we saw that quite a bunch of apps use Facebook as a means to log in into the app, and we can use that to log in automatically.
Okay, well, thanks again. So now we have the last talk for this session. As I said, we are running a bit out of time, but yeah, we can start the next session 10 minutes later than in the schedule. Okay, this time it's time for Amazon. So we're going to hear about some user-assisted code query optimization, in particular in the context of Amazon Code Guru.
Which other one?
Okay.
Yeah, the issue.
No, it's...
HDMI cable plugged all the way in.
Say that again?
We had some issue with some HDMI cables kind of falling out.
Oh.
No, it's in. No, it's plugged in. Okay, just put it down. Let's plug and pray.
Let's see the next slide. The slide is also not moving.
No.
Let's try it.
Yeah, it looks like it got stuck there.
Yeah.
Let me So I have just unplugged it. And just
So now it's
unplugged
unplugged, but then
Still in the way now?
I plugged it again, so let's see if it works now.
what
Uh,
is?
You want to unplug both here and here, or just?
So this goes here, right?
Yeah. Did you unplug here? Sorry.
That,
Yeah. Go ahead and unplug that.
the point is that the image is staying there.
Oh.
Yeah,
crap.
that's screen
bad
froze.
design.
Yeah.
Okay. Technical issue.
Fix this one. I'm gonna have to call in help.
Yeah, actually, the screen froze. I think.
Yeah, it looks like the screen frozen is frozen now.
Yeah.
The only because now it's
Maybe if you share your screen into the Discord as if you were remote.
yeah. The other way might be to share the screen through Discord.
Yeah. That would work.
Do you have the Discord
I
app
do.
installed?
Yeah.
So if you open,
Powers to do that.
yeah. So you need to
So-
enter here. What's the name of the channel? Present.
Presenter Royal.
So
And what's your handle?
yeah. Wait a second. It's opening up.
Or is there any other laptop that's working? I can try.
But it's
Well, it
not a problem
sounds
of the laptop.
No, it seems like this is a problem with some connection note for today.
I
I'm
think-
sorry.
Yeah, no worries.
I think
So the Discord is not logging in. So in the morning
Quit
I was
Discord
logged in.
and try again.
So want to see from here.
No, because otherwise we should detach the HDMI and put it straight here from the beamer, and then online there is nothing. Again.
We can do that. Help is on the way.
Okay.
Yeah, the Discord is not working on my laptop now.
Maybe should we anticipate the coffee break then?
Okay, let me try reading from here.
We may
The next session's gonna,
Mm?
the next section's gonna go along then.
Yeah, I know, but rather than waiting for 5 or 10 minutes here.
Yeah, that's a good point. We can start with the next one.
So
Yeah, I'm able to log into Discord, so I'm not
Okay.
sure if this would help.
coffee break should start right now, right?
Let me check the schedule. Yes, I can.
Okay, so guys, let's do this. We anticipate the coffee break now. So in the meanwhile, we fix the technical issue. So I would say we start again in 20 minutes. So let's say at 3:50, okay, p.m. And so we aggregate this talk to the last session.
Yeah.
And we fix the issue in the meanwhile. Sorry for that, but yeah, instead of wasting time, let's go grab a coffee and then come back earlier. Thank you.